In this informational video, we will be discussing ocean waves, their formation, and other aspects surrounding the birth of a surfing wave, also known as a surface wave or wind-generated wave. Our story begins with pressure in the Earth's atmosphere. Gaining its energy directly from solar radiation traveling through space and reflecting off of the Earth's surface. Pressure is usually measured with a barometer and is measured in either bars or pascals. The Earth has an atmospheric pressure of 1 bar or 100,000 pascals. Differences in pressure are caused by different regions on the Earth being heated unequally. This is largely due to the Earth's position on its axis, as well as the different composition of land and liquid on the Earth's surface. High pressure systems are usually consistent with clear skies and what is considered desirable weather. Low pressure systems are usually consistent with bad weather, clusters of clouds, and high winds. Differences in high and low pressure can be directly linked to the density of the air within the system. If the density of the air within the system is high, the air will sink and the less dense air will rise above it. Water in the ocean tends to be pulled from an area of high pressure to an area of lower pressure by a force known as pressure gradient force. However, the Coriolis force changes this behavior by transporting it in places of equal pressure, also known as isobars. This behavior caused by the Coriolis force is called geostrophic flow. Since the Coriolis force direction is opposite in different hemispheres, the geostrophic flow direction with high pressure in the northern hemisphere is to the right, whereas the flow direction in the southern hemisphere is left. Because of the difference in density in the atmospheric pressure, a convection current is created, and is alongside many other convection cells with differences in pressure between them. These convection cells are similar to convection currents within liquid. The higher density air sinks, whilst the lower density air rises, causing an oscillation-like movement. The resulting force from all this movement creates wind, usually within the low pressure systems or cold fronts. The resulting wind, if blowing over a body of water, causes small surface tension waves, also known as capillary waves. The size of these waves, also known as the fetch of a wave, will usually increase in size according to the strength and consistency of the wind. From here, we move on to the creation of waves, the anatomy of a generated wave, and how it moves through different depths of water. There are several different types of waves, all depending on the surrounding environment that influences their shape, power, and velocity. The different types of waves can be categorized into 3 main sections: gravity, chop, and swell. A type of wave that would be sorted into the gravity category would have to be considerably larger than a microcapillary wave, large enough for it to move due to gravity pulling the top of the wave down and the bottom of it upwards, producing a circular motion. These types of waves no longer need wind to help it move. Chop waves consist of waves that are of considerably small wavelength and very short wave period, such as capillary and microcapillary waves. These chop waves would have the potential to grow into swell if the wind generating them is strong and consistent enough. Defining a wave in any particular way can be challenging, as a wave is incredibly complex to measure. This is where the Irrbarren number is useful. The Irrbarren number is used to measure several aspects of a gravity wave, defining it as either a spilling wave, plunging wave, or surging wave. Defining a wave's anatomy is rather simple. At the highest point of the wave is what is known as the crest of the wave. The lowest point is known as the trough. In order to measure the wavelength of a series of waves, you must take the distance between either the crests or the troughs. The crests and troughs work together to produce a series of orbitals that travel with it just underneath the water. The crests are pulled downward by gravity, allowing for the trough behind it to be pulled up by the resulting force. This motion creates orbitals that extend down toward the sea floor, usually measuring at half the distance of the wavelength that it is influenced by. As for the speed of a gravity wave, deep water is where a wave travels the fastest. As the wave enters a decreasing depth, the water orbitals reach further towards the seabed. Once the water orbitals have reached the bottom of the seabed, it slows down drastically, building up until it finally breaks and turns into a whitewater wave. However, a wave's death isn't that simple. A lot can happen to its formation and velocity before it finally disperses. Have you ever wondered what happens to the energy that a wave possesses when it finally disperses and breaks onto the shore of a sandy beach? Well, the excess energy is given off in three main forms: sound, vibration, and heat. The larger the wave, the more energy it releases as it finally ends its life. Other than being absorbed by the shoreline due to a gradual inclined slope of the beach, there are other ways that a wave ends its lifespan as it comes into contact with obstacles. The main three ways in which a wave reacts to colliding with an obstacle are reflection, diffraction, and refraction. Vertical faces such as sea walls, harbors, and cliffs can cause reflection to occur. When a wave collides with a vertical face, it is then bounced back at a direction based on the angle of where the original wave came from. This usually causes standing waves, which can be reflected back into the same direction as the original source, and can possibly cancel out waves traveling in the opposite direction. Diffraction is the propagation of a wave around an obstacle, usually an island or a breakwater, whereas refraction is a wave being slowed and bent by shallow water, usually leading into a beach. There are generally two types of waves that come crashing onto a beach: a constructive wave or a deconstructive wave. A constructive wave is usually of lower wave frequency, with little to no backwash, and brings with it more material than it takes away from the shore, building up the banks and creating a steady, healthy incline to the beach. A deconstructive wave is of higher frequency and does the opposite of constructing the shores of a sandy beach. Instead of bringing material to deposit onto the beach, it takes more material away than it brings with it. Deconstructive waves also have a stronger backwash, which also helps with removing more material from the shore break. And there we have it, from the pressure systems producing wind for swell growth, to how the end product impacts the beach that it comes crashing down upon. This video has given a brief but informative understanding as to how surfing waves are made.